Okay, I'm gonna skip through the recap because we just talked about it. But yeah, so regularization is kind of a smart way to not overcurve. I mean, not overfit the data. So basically, you're kind of taking an approach that allows you to have a smaller variance. So if you think about like the mean of this, taking the average over all the lines that you might fit on this curve, you might have with linear regression, you might have a line that looks like this, but that the variance, is in this gray area. Whereas if you do it with regularization, you'll have a variance that's much smaller with respect to the average line. So I guess here, yeah, here's the bias, basically the y-intercept and the variance of these fits. Okay. So this is kind of the big sort of loss function for regularized learning. And the difference here, so this is still the same loss function. The difference here is that you add a term.
Sorry, enough of the sound went bad again. You stopped at, this is the regular loss function.
Can you hear me now?
Mm-hmm.
Okay. Yeah, so so this is the regular loss function, E theta.
I'm sorry, it's bad again.
How's this?
You're a little quieter, but it's not messy, so it's like we can understand you.
Okay. Let's try it again. Okay. So yeah, so basically we've added this regularization term that basically penalizes the objective value or the norm of your parameters. So this is the norm of your parameters, and so you want to minimize this cost function. So it's going to say like these shouldn't get too large. And in a way, we're gonna show why that happens. But by minimizing this term and by minimizing this 2 norm and saying this value of these parameters shouldn't get too large, we'll actually do some good things for not overfitting. And so we'll kind of show why that helps in this lecture. Okay, so we have our polynomial model, and we can rewrite it as this, where we just take the z's, or we just take the x's and turn them into z's. And regularizing is just a way of constraining the weights. So first we'll start with doing a hard constraint problem, and we'll show that regularization is kind of like a softer constraint. But so if we say that we have this linear model that's subject to that basically the fit, or basically the coefficient has to be equal to 0 for d greater than 2, then we'll only take basically the first 3 parameters here. So there's a constraint there, and that's not going to be good. Basically, we're just saying, okay, we only have 2, or we only have 3 values, and so we want to do something that's a little bit softer, that's not so harsh. So instead of doing that, let's let's cut them some slack. So instead of doing that, let's just say it's subject to this constraint here. And this constraint says that the 2 norm or theta transpose theta has to be less than some constant, less than or equal to some constant c. Okay. And so right now I'm just kind of going through why regularization ends up being this. And so we'll kind of talk about it towards the end, but you can ask questions about the sort of conceptual stuff as we go through. So for simplicity, let's call this theta ln as the weights solution for the non-constrained one. So basically the solution from last time where we have theta, so theta ln is going to be equal to z transpose z inverse z transpose y. So that's the solution that we talked about last time with the pseudo inverse times y. And then theta is going to be now our solution for the constrained model. Okay. And so, for example, if we took the theta 0 and theta 1 to be 5 and 10, and we only had one feature, so just to kind of take a look at what's happening geometrically, we would get a plot like this in a 3D view for the error for e theta. And if we look at the top view of e theta, we'll notice that this very bottom point here is going to be the basically the bottom of this, the sort of lowest point on this, the minimized error point on this curve. And from there, we can actually draw these contours out of larger error, but the same error. So along each of these lines, these contour lines, E is the same. Or, yeah, E is the same. No, does that make sense? Yes, E is the same along each of these contour lines, but there is only one minimum. So what we're trying to do in this sort of, by adding this constraint, is that we'll say that, okay, instead of just giving me the very, very minimum one that's right at the center here, can we get another one on one of these other lines that also satisfies another constraint that I have? Okay, so so this is E. So just looking at E, we can draw these contour lines that say, okay, we have the same error in each one of these contour lines, but how can we use that to help us? Okay, then if we look at our constraint, which was...
I'm sorry, Elsa, can you go back to the plots? Because I don't think I understood what was being plotted. Like,
so this is...
what are the colors?
What are the colors?
Yeah, what do the colors mean?
I don't know what the colors mean. I mean, I guess green is lowest and red is highest.
Error?
Yeah. This is this. Surface plot of this. So
And
I think...
then the contour lines represent the place where the error is the same.
Yes.
Would you say is the error going to be the same within bounds? Like when you say like the expectation is the same.
It's not expectation, it's error.
Oh, okay, yeah. The when you say that the error is the same along the contour, is that literally like on that contour itself, or like the area between two contours have the
No,
same?
on the contour itself.
Oh, okay.
Okay, I guess, yeah, the red line on the left makes sense to me because that's all the same color. The black lines on the right don't make sense to me because it's along different colors.
Yeah, so it's the top view of this entire thing, right? And so you can imagine these as like slices of this 3D shape. where if you take this function, and at each point on that line, you take whatever the x coordinate is and the y coordinate is, and you plug it into this function, you'll get the same error at each point on that line. So imagine like you just slice down this this 3D model, and you're just considering some like oval that you're taking a slice of.
Yeah, I guess that part's confusing me because it's I would expect along that line the colors would be the same.
Okay, so maybe I can explain it looking at um, yeah, so yeah, I mean, I don't really know how else to explain it. So I'm saying that like at each, so like if this was, where's x and y? Let's just assume oh, I think I guess I see your point. If you look at this point. Okay, so I guess I'm not sure if these lines are actually representative of of what I'm saying, that the E is the same, but I'm saying that there are some contour lines that you can draw here where the E is the same.
Okay.
Yeah, so I guess I don't know that, like, because I think he just kind of like drew something, right, to kind of represent the idea. But there are some lines that you can, so they probably don't look like this per se, but there are some contour lines where the error is the same.
Okay. Either that or maybe these are the change in there. I don't know. Okay.
Well,
Because I guess like when I think about topographical map.
oh yeah, okay, yeah. So I guess the change, yeah, the gradient in error is the same.
Okay.
Along these lines.
Okay.
Yeah, that's actually important. Yeah.
Okay.
Does that help? Does that make more sense?
Yes.
Okay. Yeah, I think that's it. Yeah, these are gradient lines.
Okay, this makes a lot more sense.
Yeah, but I mean, I still don't. I guess if you're still looking at the colors, well, yeah. Again, this might not be like an accurate contour lines, but that's the idea. Is that like there are some contour lines where the gradient is the same.
Plus, it didn't even really tell you what these colors represent. They might just be literally to designate some sort of, like, I don't know what the point of them are. Like the colors.
I think they're the error value. They're the z value. So like up here is like sort of the max error.
Z possible value.
Yeah,
okay.
and down here is the minimum. Okay.
Yeah. Okay.
Okay. Yeah, that was important. So yeah, so that's kind of the same thing that you can do. So we did that. So now we've done that. We've created a gradient error, and now we're doing the same thing for the constraints. So the transpose of the theta transpose theta. That is just like if we take this theta and we take the transpose of it and multiply by theta, then we'll get this equation, which is just theta squared, theta 0 squared plus theta 1 squared. And remember that we're saying that this has to be less than or equal to C. So one thing that we'll see is that, just from like our mathematical knowledge, we know that this is the equation of a circle, right?
Yeah.
So we're noticing that this is basically giving us some circular bound on like what these values are.
Oh, okay.
And so if we take the gradient of this theta, we'll get a vector that looks like this. We take the gradient with respect to, or the partial with respect to theta 0 and the partial with respect to theta 1. And then we'll get the solution is this, 2 theta 0, 2 theta 1. And that's just proportional, it just has some proportionality constant to theta 1, and theta 0 and theta 1. And so this gradient is going to be a vector field that looks like this. And so I guess in this case, yeah, this is kind of validating the same point that you made in the last slide, Stu, that if you take a contour of this, all the gradients lines of that should be, the same.
Oh, yeah, you can see that.
Yeah.
This actually is a lot more clear.
Yeah. So, yeah, okay, so that's what is getting at there. And so I guess this is another image of this, yeah, happening. And so now you can see the gradient lines are just these concentric circles.
Mm-hmm.
Okay, so now we want to bring those two together. So we have this E subject to this constraint. And so I guess this is what was confusing me, because here it says that E theta is constant on the surface of the ellipsoid. On the surface of the ellipsoid. So we're saying we don't agree with that, right?
Well, what do you mean we don't agree with?
So this says E theta. So we have this ellipsoid that represents, so this is kind of the, so remember this is our sort of best solution, theta ln. So if we assume we just have two thetas or two parameters here.
Mm-hmm.
And this slide says that E of theta is constant on the surface of the ellipsoid. And so I took that to mean that at every point on this ellipsoid, E theta is the same.
Yeah, or like at least the...
But I think we just said that that might not be the case. But the gradient should be the same. Okay, so let's just look at the circle.
But if the gradient is the same, that means that the amount it's changing is constant, right? So
yeah.
So that could still mean that the actual errors themselves could be different values, but the total change of that is the same. So, but this is saying that the actual error on the entire surface would be, well, it looks like it's greater than 0 and constant.
Mm-hmm.
And does that really make sense when you look at the images like that in the slide above? You can see that there is like, you can see that that's not the case unless...
Well, no, I mean, if we look at the circle, that is the case, right? Because the radius along each one of these is constant, right?
Right, yeah, but just because the radius is constant doesn't mean that the magnitude of those errors are constant.
But I guess it kind of does, because in this picture, when you go along the circle, the
The
color is
colors
the
does
same.
change.
Well, I mean, if you just look at one circle and you
It's
trace it
uniform.
around its um, perimeter, you see that the color is the same. I'm not sure if this is. It looks like it's different for some reason. Like before, it was arbitrary, but now
Oh,
you
okay.
see,
So
the difference.
yeah, yeah. I think what they're saying is true, and it's just like a poor. It's supposed to be uniform, but the color looks off to us because it's just a bad rendering.
Well, I think maybe here they drew them arbitrarily, and then when we skip 2 slides, now they make sense. Or maybe actually, I actually have no idea what I'm talking about.
Yeah,
Well,
I mean, it's not
this
that. I don't know if it's actually that important. It's just to kind of get an idea of what's happening. So I don't know.
at the very least, you can tell that with the vector field drawing, you can
Yeah.
tell the colors are all the same within a certain concentric circle.
Yeah.
Maybe there the colors mean the gradient. I don't know. Whatever.
Yeah. So yeah, I mean that doesn't matter. But basically, what we're trying to say here is that that if you want to find a solution that is subject to this constraint, so this constraint is represented by this circle here, that this theta t theta is on this circle, and that you have some value. Yeah, so I think that those do have to be equal error lines, contours. That the error here is constant along this surface, then what you can do is you can take the gradient of both of these surfaces. So if you take the gradient along this ellipse surface, it's given by this line, and you can also take the gradient along at some point of this circle, and the point where you would have both of those things be satisfied is the point where they intersect, right? So you have some error line that's intersecting with the constraint line. So basically, I mean, if I had this circle sort of be larger than the ellipsoid, then I would have like basically like all these points, right, are fine, right? But the place where it's optimal is when you get the minimum error that satisfies the constraint, and that's at this point here. And something else that's also happening at this point is that the gradients, since the gradient's always perpendicular to that surface, so that there has to be a perpendicular gradient to the E surface and a perpendicular gradient to the circular surface. And so we basically can tell that, you know, the gradient of E is proportional to the negative gradient of so basically if I like flip this around and gave it some proportionality constant, I would somehow get the E, right? So if I flip this red line around and scaled it by some value, I would get E. So in this case, it's theta in this case because the gradient of theta transpose theta, remember, was just like proportional to theta 1 or theta 0 and theta 1. So we can just say it's proportional to theta, right? And so he kind of does some or I guess there's some magic here, right? So you say you know we get to choose this proportionality constant, and so let's choose it to be 2 lambda over n. So lambda we get to sort of play around with, right, to make sure it matches. 2 we can just choose 2, and then n we can choose n to be one of the values of that proportionality constant, as long as we can play around with lambda. And so if we write this as now the relationship between those two gradients, we can then subtract, or add this to the other side, and then we have this like this. And then if we integrate this equation, so remember these are basically derivatives, right? So this is a gradient equation, this is a gradient equation. So if we take the integral of that, then we would get the actual E from the gradient there. And from this part, remember this is theta, this is a vector, 0, theta 0, theta 1. So we take the integral of that. It would be, the theta squared if we were just like have a regular scalar here, but now it's the vector, and you still divide, or it's theta transpose theta, which is basically equivalent to our theta squared in scalar terms, and then we divide by 2. So in this case, the 2 drops out, and then we just have this lambda over n. And so this is you note that this is the same equation that we talked about as sort of the governing objective for the regularization term. So what that kind of means is that we now get to sort of get away from this absolute sort of minimum. So by constraining that, like, theta has to be by constraining that theta has to be like some value. So I guess this constraint, what the argument is that this constraint is, or this adding this onto here is equivalent to having a constraint of theta transpose theta less than or equal to c. Mm-hmm. And so we're imposing, basically by adding this, imposing a constraint on the problem that says I need to also have that, you're a little bit away from the absolute minimum, and how far away you are from that is determined by this c value that I put here, right? That's what kind of we just showed with the geometric argument. And so that's what this is doing, and that kind of gives you a little bit of a intuition as to how this is going to regularize the solution and pull it away from that sort of absolute minimum. Any questions on that?
No.
Can you actually just go up one more slide one more time? Because I didn't realize we're looking at 2 different circles when we're looking at those colorful plots.
These?
Yes, one more slide. Okay. Another slide, please. Okay. I see.
Okay.
And so theta transpose theta, this is supposed to be like conceptually, is this error? No, it's not error. It's, what word would you use for it?
This theta transpose theta.
Mm-hmm. This conceptually, because we took the gradients. This is supposed to be like some gradient representation, right?
Yeah, I mean, conceptually, it's a circle, right? And so I think this is getting at why that. So it might be the case that both on these contour lines, both the gradients are the same all the way around, and that the actual value is the same all the way around. Because this theta squared, theta 0 squared plus theta 1 squared represents these circles, and so I can just set it equal to some c, and each one of these has to be that constant, right?
Yeah. Okay, I think I'm starting to make sense of this. I guess we're constraining the options for our thetas such that they meet this requirement of their gradient representation equaling c. And we're comparing that to our actual data. So that's the ugly ellipsoid.
Mhm.
And we're doing, I guess now the regularization is saying that we're going to only pick, okay.
Mhm. Yeah. So yeah, I think that makes sense. Um, yeah, he was like sort of drawing some stuff here. Yeah, basically like that, like it really um, you have some choices when you choose this C, and this. Well, I guess you don't really choose C; you choose lambda. But you know that as there's an inverse relationship between the C and the lambda. So as you decrease lambda, your C gets larger. And so that as your C gets larger, you'll note that you get sort of closer and closer to this point. And if you get large enough that you pass it, then that point is within your C. And so you'll just always choose that point, and it won't you would basically take out the regularization effect. So you have to choose your C strategically, or your lambda strategically, such that you're not also encapsulating the sort of optimal or minimum point. So I guess if we hmm, well, I just had a thought that maybe the answer to this question is that, like, you can still you can constrain the thetas such that, yeah, actually this is yeah. Okay, yeah, so that's kind of the idea. So like you are, as you're increasing this circle, you have different sort of points that you land on, and there's different so it'll just find this line, right? This error line, such that you have this equivalency as you cycle through your um, different lambdas. So you can imagine there's like a billion of these, right? In between all these, it's like it's continuous. So there's like a billion of these lines. Um, so yeah. Any other questions about that? Okay. You guys still hear me okay?
Hmm.
Okay. All right. So I think that's what we call ridge regression. Because I couldn't. I've been trying to figure out what the difference is between this and what we've done before, but I think we just name it as ridge regression. And um, I think there was an article that talked about a little bit more. Yeah, actually, maybe I can pull it up. It talked about how you can sort of formalize this process by calculating some um, some variance over and doing like some multiplicative noise thing. It's not that hard, but there's like a formal way to do it. But I think the whole idea that he comes back to is that both that method that he was using, and just setting um, this n times the variance squared equal to lambda is the same thing as yeah, you can basically just set this equal to lambda, and it's the same thing. So this is just a formalized way, if you have some data, to choose what the lambda is, rather than just like shooting in the dark and choosing some random lambda. So I would go ahead and read this, but like it's basically the same thing as just choosing some lambda, but a formalized way to do it, and by using the variances of the data. So that, I think, is what they're sort of trying to get at here. And then so I guess this is interesting. So in this case, after you choose this lambda, you can then still write this as a one-shot sort of regression problem. So if you write your regression function now like this, as we've seen before, this f of x theta, then you can kind of write in, all the different matrices. So you have your Z matrix here, which we'll call the design matrix, and you have your theta matrix, and you have your observations Y. And so basically, now you can write this as, the sum of your errors plus your regularization term. And if we want to write that differently, we can just write this as yi. Sorry, not that as yi. This is yi. So it's squared, so it's the same thing. If I write the yi minus this or this minus yi, same thing, it's squared. So it's the same thing. And then now we take the derivative of this error term and set that equal to 0. And so you can see here that, so this is just, remember this is theta transpose theta. And so if we take the derivative of this, we'll get, with respect to theta, we'll get this form here. And I haven't gone over it, so I'm just trusting that this is right. And when you work that out, when you set this equal to 0, and you work that out, you'll actually get a closed form solution for theta, where now all that we've changed is we've added this linear, this regularization value times the identity matrix, where the identity matrix needs to be the same size as this, your dimensions basically. So your identity matrix is going to be d by d, I think. Yeah. And so then you have kind of a one-shot regularization solution using whatever lambda you choose.
Okay, and this is basically like what we looked at for the linear regression, except now we can't do the pseudo inverse anymore. Or actually,
yeah, now you can't do the pseudo inverse anymore.
Okay.
Yeah, you would have to actually compute this inverse first and then do that. So yeah, so if you don't, so yeah, I guess this is saying if you're not making a regularization, if you're not making the function regularized, then lambda is 0, and you can just do the pseudo inverse of this thing. But adding this term improves the conditioning of the inverse, since if Z is not full rank. Oh yeah, that's actually quite interesting. Yeah, because if Z transpose Z is not invertible, then adding this will actually make it invertible. So you can, yeah, so that actually improves how well the matrix is conditioned, that you're going to be taking the inverse of. So that's kind of a nice thing here. Okay, and then it says as lambda approaches infinity, theta approaches 1 over lambda times this, which approaches 0, because this goes to infinity. Okay, so what does that mean? So we saw here, or we mentioned here, that as theta, so theta and C have a inverse relationship. And so if you increase, or lambda and C, sorry, have an inverse relationship. So if you increase lambda, then you decrease C. And so you basically are just pulling this towards the origin. And if you have it high enough, then your theta is just going to be 0. So you don't want lambda to be too high, because then you get nonsense. Okay, I think we'll skip this example. We're kind of running short on time, so. Okay, but this is, okay, I guess this is actually interesting. So we had this same curve, I think we wanted to fit earlier. And so you can see the different fits for the different lambdas. So this is lambda 100. It just gives you basically a flat line. 0.001 gives you a better fit. And then as you decrease it further, you kind of get closer. But here we're using d equals 7. So before it was d equals 9, but d equals 7 is pretty close to d equals 9. So you're kind of fitting more of the points as you're decreasing lambda. But you're still ensuring that it's at least a little bit, I guess, generalized. But yeah, I guess you still don't want lambda to be super low.
So lambda is our smushing factor.
Mm-hmm.
Cool.
Lambda is our smushing factor. Okay, so here's d equals 3 and d equals 5. Okay, so that's it for ridge regression. And this is kind of a review of that. So now let's look at another regularization choice. So instead of using this, so this before the regularization term, we set it equal to the 2 norm of theta. But what if we set it equal to the 1 norm of theta, which is just going to be given by the absolute value of theta. Okay. So now instead of having this circle, we have basically like a diamond or a square, where this is now your C, right? So this point is your C here, here, and here. And so what this enables you to do is to basically set one of the parameters equal to 0, and kind of solve for all the other parameters. So this is yeah, I mean, this is an interesting way to like sort of select the features that you want to look at in your regression function, right? So you can just neglect some other ones by doing this lasso regression and just setting those equal to 0. And the way you do that is just by changing what the regularization term is, the norm of that term. So lasso is an acronym for least absolute shrinkage and selection. Okay, does that make sense? All right, and then last thing here is determining regularization strengths. He purposely kind of, and when I was watching the lecture videos, kind of skipped this one, but I'll still explain it, and I'll explain why it's bad, and then we'll talk about the other one. But so basically, one way to do this, the determining how good your regularization term is, or like how good your model is to do some cross validation. And so what you can do is you can loop through all the data points that you have and train the model on every single point except the point at I, so just leaving one point out, and then compute the test error on the held out point. So like you basically use that point that you held out to test the model. So you basically say, okay, how close is the predicted model using all these other points but the but the so basically like test and train, right? You have some training set and you have some testing set, but in this case you only have you only use one data point as your testing set, and you train with all the other ones, and then you average all the test scores and see how good that model is. Versus what I think is more common is where you split the data into subsets or folds. So each one of these K subsets is going to be a test set for each iteration that you run. And so instead of training the model on everything but just one data point, you train the model on every fold, every sort of subset except one of the subsets. So every other subset is your training subset, and one of the subsets is your testing subset. And then you compute the test error on that testing subset, and then you average the test errors. And then you take basically the highest one. Or the one with the most matching, the one with the most matching. Okay. Yeah, I'm not sure what this is getting at. Pick up lambda with the lowest mean value of root mean square error calculated by the cross-validation approach. Okay. Yeah, so I guess this is saying that you can like try different lambdas and then choose the one that has the lowest mean value of root mean squared error when you are, while using this test and cross-validation approach. Okay. Questions? Okay.